Okay, everyone, thank you so much for coming. This is the Dawn at Ceres press briefing. I'm Liz Landau from NASA's Jet Propulsion Laboratory, and I'm pleased to introduce 4 members of the Dawn science team. We have also many new images and video available on our website at nasa.gov/dawn and dawn.jpl.nasa.gov. Today's speakers are Carol Raymond, the Deputy Principal Investigator from NASA's Jet Propulsion Laboratory. We have Ralf Jaumann from the Framing Camera Team at the German Aerospace Center, DLR. We have Maria Cristina De Sanctis from ENOF in Rome, Italy, from the VIR team. And we have Tom Prettyman from the Grand Instrument. So first, Carol will give us an overview.
Okay, welcome everybody. We're excited to share with you some of the recent results of our exploration of Ceres. I'm going to start giving you an update on where the mission is right now. We began our low altitude mapping orbit in mid-December, and we've now, just this past week, completed 2 global mappings of the surface. And in this animation, you're seeing how the coverage laid down orbit by orbit in this methodical mapping. We're now into the second global mapping where we try to pick up all the gaps that occurred in the first because of the inability to exactly predict where the orbit is going to be weeks in advance. And so we planned out these 2 complete global mappings to ensure that we could cover every inch of the surface. Now, you notice that our favorite crater, Akator, which we'll be talking about today, had a gap which stubbornly persisted almost to the very end. And so we were all anxiously awaiting that last score to be filled. And finally, it was, yay! And then we actually had to do a little tweaking just to make sure we picked up the last little bits. But as you can see, we accomplished the goal of covering the entire surface at this resolution of 35 meters per pixel, or about 115 feet. And we've now seen some incredible detail, which is going to be the subject of study for quite some time. So we're going to visit a few areas on the surface, talk about what we're seeing, and I will begin with looking at the Akator crater. You're going to see this enhanced color image to give us our location on the surface. So I think everybody already knows that Akator is the home of the very bright material on Ceres. And here in an image from our high altitude mapping orbit, in an image which has color from the observations we were able to make in the HAMA orbit, you can see Akator has a fairly irregular scalloped rim. It's an example of a complex crater. It's about 92 kilometers in diameter and roughly 70 or 80 million years old. It has it may be a little hard to see, but it has a bluish crater floor, and the surrounding materials and the crater walls show a more reddish tone. So there are some color variations which would be indicative of some compositional or perhaps also physical differences between those materials. So now we are going to zoom in, and here is an image from LAMO, and you can see now the bright spots are saturated, and so we can see a little contrast in the surrounding materials. And what I want to point out here is there is a albedo variation in the area surrounding this crater. It's much darker up in the northwest to the upper left, and generally brighter in the lower, so that's upper right, lower left. So there may be some more regional changes in the properties of the surface as well. Now, zooming in, we can see a lot of the features of the crater. Again, the very irregular scalloped rim. We see, if we look at this as a clock, over at 3 o'clock, you can see a whole set of terraces where material has slumped from the crater wall into the crater floor. In general, we see a very flat, smooth floor in this area right here, and a much more irregular, hummocky surface up in this area. And you can probably make out there's some flow fronts. So we see material has been flowing on the crater floor. And we also see areas where we have some, what looks like some more solid material that's cropping out in the walls. Now, of course, everybody concentrates on that bright spot there, so I wanted to draw your eye away from it for a moment. But here we started to see how complex the distribution of the bright material is. And the central complex is about 10 kilometers across. And it's composed of a very bright center and then some surrounding areas. And then we have the complex of smaller bright spots over here in the side wall, or the side of the crater floor. Now, if we look at this with a different contrast, so now we're not saturating the bright areas, and that's why the rest of the surface looks so dark. We see that we have a very complex structure within that central complex. There is a dome right at the center, and then material has filled in the depression, but there's a lot of irregularities in the central pit wall. As well, the subsidiary bright spots, you can see, are much less bright. The difference in brightness is a factor of 2 between those spots outside and the central pit. And this is a very diffuse set. And you should also be able to see, I hope, there are a lot of fractures that run through this area here. And we see those fractures elsewhere throughout Okator crater. And then finally, if we zoom way in, here you see, zoom in on the central pit with color from the HAMO data that I began with. And a couple of things pop out. The central dome has a different color tone than the surrounding material. And we also see these concentric fractures that define that central pit area. And in general, the distribution of material is quite irregular surrounding the dome. So the fractures on the dome are rather radial. So the fractures, patterns, the difference in the color, and the overall geomorphology are suggesting to us that this is some recent activity within this crater, even though the crater is not that old. But it appears that material has come up from below and been emplaced in the central pit. So we're investigating whether when this process occurred, whether it was recent or it just is such, the material is just so different in character and that can explain its brightness rather than its recency, and by what process that material came to the surface. So we see bright spots elsewhere on Ceres, and so this is not a process which is unique to Okator, and Ralf is going to tell us more about that, so I'll turn it over to Ralf.
Oh, thank you. So, of course, Okator is one of the most amazing features on the surface, but there are other features which are also puzzling and which are similar to Okator, or they are some kind different from Okator, making Ceres a very geologic interesting object. And another feature which has also this bluish interior is Ikapati, and here is the 70-meter resolution image of Ikapati, and you really can see that there is a twofold feature in there. So we have a regular impact crater in this part with all the slumping from the crater rim. We have a very developed crater rim, and we have a very smooth part in this area. And the smooth part is also of this kind of bluish color. And if we compare this and go a little bit closer to it, then we start to see that there are flow features, low-bed flow features coming out from the interior and going over this crater rim here. So there is some kind of resurfacing, but it gets more complicated if we go even closer, and we really see there are pits. These pits are not impact craters. These pits are depressions where we expect that volatiles has been evaporated, and the material then has built the pits. And if we go even closer, we partly see that these flow features have different levels. So we have here flow features and here flow features. And in between, we have the smooth plains, and the smooth plains covers flow features. So it's not only one resurfacing which happened here, it's two or more parts of resurfacing. And the whole area, which is smooth and show the flow features, has this bluish characteristic in the visible colors. But that's not the only thing which puzzles us. There's another feature which is a mountain. And if you look at the color at this image too, then you really can see it's the mountain. The mountain has about 5 kilometers, about 20 kilometers in diameter, and is about 4 kilometers high. It's very close to this impact crater here, and we will see in a higher resolution that we don't have any connection, geologic connection with this impact crater. But the most interesting thing is that we also see the blue stuff. And that makes it difficult to explain the blue stuff, because if you look at the impact craters, we can say, okay, the blue stuff is smooth, has flow features. That's like impact melt. But this mountain has the same spectral feature and is obviously not impact melt. And if we go closer, then we pretty see that at the closest part, we see that the mountain is really coming out from the subsurface and taking the surface features, which are a little bit older, up this the mountain rising here. So that really makes this mountain, let's say, a little bit unique in the solar system. So, and it makes it also unique on Ceres. We have other mountains, but they are not developed in this clear sense, but they seem to be older. So, and these features seem to be very young. So there is a connection between the surface and the subsurface, and the mountain and the impact craters we have shown so far really show that there is something in the subsurface which is different from the surface. And the last feature we can see is a very young impact crater. It's called Haulani. It has a size of 32 kilometers. It's about 3 kilometers deep. And you see again the bluish stuff, and here you see that the blue is different. So the brightest blue is in the center, and if you go to the ejecta, the bluish stuff is getting darker and darker, but it still is blue. And if we go closer to it, then we see again it's like a crater, a classical impact feature, but it has a mountain ridge in the center, and it has a very smooth surface in the center. Even going closer, you can see there are almost no impact craters on this crater floor, showing that it's very young. But we again see some kind of pits, means outgassing vents in the center of the impact crater. As Icapati, we don't see too much fractures on the surface, though that's probably seems that the surface either is covered by very smooth material or the fracturing didn't occur. And if we go closer here, then we see that even outside we have flow features, and a lot of flow features which are channelized and which show some kind of low-bed flows. So this material, which has been thrown out by this impact crater, is very mobile, and in particular, Haulani also shows compositional differences, and in order to explain this, I hand over to Christina.
Thank you, Ralf. So, again, on this particularly crater on the surface of Ceres, and these images are taken with the VIR, the mapping spectrometer aboard on the mission, and VIR is a an instrument that, differently from the camera, is able to couple the information on composition and the information on the surface, putting together the imaging capability and the spectral capability. On the image on the top, in this one, you see the projection in red, the projection of the data that we acquired, while in all the images below are taken the projection on the data itself with the VIR data. And VIR is an imaging spectrometer that works in the range between the UV to the infrared, and is able to acquire data in more than 800 colors. So while the camera has only 7 colors, we here can see the surface of Ceres in much more colors. So in this first image here, you see colors in the reflectance in the infrared, and this is done on particular colors, is done on purpose to highlight the difference in reflectance. So you are able to see the internal bright material that also Ralf showed before, and the dark stuff that is around is the craters, the dark ejecta. While in the middle, in this image here, we make a color composite using different band ratio. What it means? We use different colors, and we use the ratio between different colors to highlight the differences in composition. In this image, the reflectance information, the albedo information is gone. There is no more albedo information inside, but there is only the contrast between the colors that tell us about the composition of the surface. And in particular, this image has been done with 3 colors: red, green, and blue. The red colors means larger abundance of phyllosilicates. The green colors means larger abundance of ammoniated phyllosilicates, and the red one is more on the reflectance, so give us a little bit of level of reflectance. So in this image, in these images here, you see very well that inside the crater we have a prevalence of green, light green colors. That means ammoniated phyllosilicates is a little bit more abundant with respect to the surrounding material that has this purple, deep purple colors. That means that we have less phyllosilicates and less ammoniated phyllosilicates. And at the end, because VIR is able to go far in the infrared, up to 5 micron, we are also able to retrieve information about the temperature of this material. So this last image has been done using 3 colors again, and the red colors that you see very well in this part of the image, the red colors is the colors that give us the information about the temperature. So red means very high temperature, and blue means very low temperature. And these craters has a very strong contrast between inside and outside. Inside the craters we have a lower temperature with respect outside the crater, and I have to say that also during the approach Ceres, this Aulani crater stands out as really an anomaly in terms of temperature, because it really was coming out as a dark spot in the mapping on the temperature maps that we had. So Aulani is really a very young crater with a lot of stuff inside, a lot of information that we are starting to understand, and thanks to the new data that will be acquired soon on Aulani in these lower orbits, I think that we can disclose a little bit more the origin of this material. And up to you.
Thank you, Christina. I'm pleased to report that GRAND has functioned flawlessly since it arrived at Ceres, and we're now positioned in a low altitude orbit where we can begin to sense the composition of Ceres Surface. And so, since you haven't heard from us in a long, long time, I'll take a moment to reintroduce you to the idea of what nuclear spectroscopy does and how it's used, and show you some preliminary data. So the chart that you're looking at illustrates galactic cosmic ray interacting with a planetary regolith, and there are about 4 of these particles per square centimeter per second in space. And so they're crossing into the surface sort of as a random stochastic process. They have very, very, very high energy, and when they strike the nucleus of an atom, the nucleus will explode, and it produces a spray of secondary particles, which is illustrated here. So you get neutrons and protons come out, a lot of neutrons. The neutrons will rattle around in the surface, colliding with other nuclei, and some of them will escape. And on the way, if they encounter a hydrogen atom, the nucleus of a hydrogen atom, they can lose a lot of energy in that interaction. And the reason is pretty simple to imagine. So you can think about playing a game of billiards and imagine what happens when the cue ball strikes the 8-ball head on. Well, the cue ball stops and the 8-ball takes away all the energy. And that process is happening in the planetary regolith. And so the neutron will hit the proton in the nucleus of a hydrogen atom, and it can stop dead. So what we do, and we know that the slowing down, accelerated slowing down process that you have with hydrogen in the surface, we obviously understand that. So we set up our detector to kind of monitor neutrons in a range where they're slowing down in the surface. And it's that energy range, we call it the epithermal energy range, that we use to sense hydrogen in the surface with neutrons. So the first thing you should know about neutrons is they're affected strongly by the presence of hydrogen in the surface. They also undergo a variety of other processes that affect the population, the number that leak away from the planet, such as neutron capture, and they're sensitive to regolith bulk parameters. Neutrons also on the way to slowing down and either thermalizing to be captured or escaping undergo collisions at high energy, and these make characteristic gamma rays that can identify the target nucleus that was struck. And they can also, when they get to lower energies, undergo capture. Gamma rays are also made by radioactive decay, so you have radioelements like potassium and thorium inside the rocks, the silicate minerals in the surface, and those are traces of various chemical, geochemical processes that might be going on at the surface. It's important to understand that gamma ray spectroscopy is true spectroscopy. You're looking for peaks in a spectrum, and those peaks identify very specific elements that would be in the surface. The other thing that there are two other things I think I'd like you to take away from this. One is that we're sampling about 1 meter below the surface. So we're integrating over that top meter of the regolith. So it's below the optical surface. And in that sense, it's complementary to the optical spectrometers. Another way it's complementary is that these cosmic rays are coming in from all directions in space. There's no preferential direction for them. So we don't need sunlight to make our measurements. So even if it's completely dark, we're going to be able to say something about the elemental makeup of the surface materials. So now we have this picture of how neutrons and gamma rays are coming out of the surface. How do we detect them? And this is GRAND. It's a cutaway view of GRAND. And you can see the direction GRAND points when we're acquiring science data. And you're looking at a neutron interacting with one of our outboard plastic scintillators. And so the scintillator is a transparent dielectric, so it's transparent to its own emissions. And what you do is a neutron comes in, it will undergo a nuclear reaction with some element that we load in that loves to gobble up neutrons. You get charged particles that are made. You produce a flash of light, and I've drawn the path of the photons that take through the scintillator, and eventually they arrive at a photosensor. In our case, we use photomultiplier tubes. So now let's put it all together. You've got these cosmic rays in space. They're whacking into the surface, producing, randomly these neutron and gamma ray emissions. The neutrons and gamma rays travel out to orbit where they're detected by GRAND. And so you're counting these events. And we can identify neutrons in different energy ranges. And that information is used to figure out the composition of the surface. Now, the other key thing about nuclear spectroscopy is, and it's also a difference between the optical spectrometers, is its placement in orbit dictates how wide a field of view it's going to get. The closer you can get to the object that you're measuring, the finer the spatial scale you're going to be able to resolve on the surface. Now we're at 1.8 body radii away from the surface of Ceres, and I've drawn some of the orbits and I put the cartoon of the spacecraft at one point. And at that point you can see Grand's field of view on Ceres. It's the extent of that blue paintball mark that I put on Ceres surface. So it's a very wide, it's almost hemispheric. Not quite, but almost hemispheric. The resolution is more represented by the yellow ring around the central mark, central red mark. And that ring is much larger than the individual craters on the surface. So Grand has broad spatial resolution, hundreds of kilometers, compared to the tens of meters that you can get with the other instruments. The other thing about being close is that if you're far away, you'll be seeing radiation from other sources, like the spacecraft itself. And so you have to get up at least this close in order to begin to sense the composition of the surface. So here's some preliminary data. This is a map of neutron counting data. And we're looking at the northern hemisphere Ceres, and remembering the spatial resolution. Obviously, the color is the Grand data, and it's been superimposed on a framing camera shaded relief. So don't confuse the craters with what Grand can resolve. And what we're seeing is rather interesting. It's very intriguing. You can see high neutron counts near the equator, lower neutron counts near the pole. It may be hard for you to see, but the pole is marked by a white line. But just imagine that the North Pole is kind of in the center of the blue area. And we know that Ceres surface has minerals of hydration on the surface. We suspect Ceres contains water ice. And there's a long-standing prediction that Ceres could have a subsurface ice table in the northern and southern hemispheres. And this data will allow us to test that hypothesis. So let me conclude by again stating that I'm really excited now. This is just the beginning. It's taken a long time to get to the Grand data because we had to get to the low altitude, but boy is it a wonderful data set. So I'm going to hand it back over to Carol. Pass that down.
Thank you. So we're going to conclude with a video that's been produced just to give you a reiteration of some of the comments that were made and just a nice view of the whole surface. And this is narrated by our mission manager, Dr. Mark Raymond.
This is Ceres, the dwarf planet that Dawn's been orbiting for more than a year now, providing us with fascinating views of an alien world. During its exploration, Dawn has moved closer and closer, allowing us to get a broad overview and then see exquisite detail. This is Ahuna Mons, the highest mountain on Ceres. Towering in an otherwise unremarkable area, it seems very odd that it rises so sharply, and geologists still don't know why. On its steepest side, it soars 3 miles, higher than any peak in the continental United States. Haulani Crater, one of the brightest regions on Ceres. It's about 21 miles across. Its well-defined shape indicates it's relatively young, the impact that formed it having occurred in recent geological times. You can see a substantial amount of bright material, which the latest analyses indicate may be a kind of salt. This is Osho Crater, which shows more of this intriguing bright material inside and out, as well as a peculiar shape. At 6 miles in diameter, this is the second brightest feature on Ceres. You can see next to it an intriguing linear feature called a slump, where a mass of material has dropped below the surface. This is Urvara crater, about 105 miles in diameter, although not the largest on Ceres. Although many craters have a mountain in the center, Urvara has a prominent double peak, surrounded by rough terrain and linear parallel grooves. The Kator crater, 57 miles across and 2 miles deep. As dawn closed in, what initially looked like one spot became two and eventually a multitude of features. This reflective material makes it the brightest region on Ceres. The crater also appears to be among the youngest on Ceres. Dawn mission scientists estimate its age to be about 80 million years, which is quite young in geological time. Dawn is now orbiting only 240 miles above Ceres, which is closer than the space station is to Earth, and it will continue to return spectacular views.
Okay, well, many of the images and videos you saw today have never been released before, and it's very exciting for us to share them with you. We'll now take some questions. Yes, in the front?
Eric Ham with Science. I guess my question is for Carol. Going back to Cater, that's how you say it. Wonderful descriptive detail. I'm hoping to get some more interpretation from you all. You've already reported water vapor in the crater, and your suspicions are maybe that this bright material are mineral salts. Can you give us a plausible story for how this fractured dome could have ended up leaving these reddish bright materials there, and how it connects with the presumed ice in the subsurface?
Yeah, okay, so clearly we have a lot of work to do to put together a self-consistent story amongst all these different data sets. There is a sort of general background that would indicate the heat of the impact process combined with the volatile-rich nature of the subsurface, meaning salt hydrates, water ice, mixed with rock, would be mobilized by impact heat. So that's a theory or a hypothesis that we're investigating closely to try to explain whether we could get enough heat for a long enough period of time, what type of material would react to that amount of heat and become a cryomagma, basically an ice or salt-based magma that could come to the surface and produce the kinds of strange features that we're seeing. And one of the issues that is a bit of a paradox is that the crater, as you saw, is dated to be about 80 million years old. The bright material is extremely bright, and it's hard to keep things bright on a planetary surface over time. So, I would say suffice it to say that we have a lot of work to do to work out the detailed composition of the different areas even within that crater, tie it back to the physics of the impact process, mobilizing subsurface material, and then trying to explain the persistence of that bright material over time, over geologic time. So it's not a direct answer to your question, but hopefully gives you an idea of where we're going with that.
Yes.
Eric Berger with Ars Technica. So along the same lines, a question for Thomas about the GRAND instrument. Same kind of question. You say it's a wonderful data set, and I understand you just starting to look at it, I assume. But tell us what you can about what's there that surprised you, what's not there, what can you say from this data about the possibility of a large ice sheet underground?
Right. That's a great question. It's true, we've been accumulating now for about 3 months, but then there's also the analysis cycle that follows that. And so we have enough statistics with GRAND to begin making maps and to start studying the surface. And I think it's safe to say, I'm comfortable saying that we're going to be able to test the hypothesis I mentioned, that there could be ground ice below the optical surface at high latitudes. Details of that are tangled up with other things. For example, the signature I showed you is not just sensitive to hydrogen. It's sensitive to other elements that might be present. So in order to really figure out what's going on, we have to do the complete analysis.
How long do you think that'll take?
Not long.
Not long?
Yes, sir?
Mark Road for an aviation and space technology. I know there's some operational constraints on the spacecraft with the gyros and the amount of fuel that's left. How long is this mission going to last with that handicap? And what about funding for an extension if you need it to do the kind of analysis that you spoke today? What kind of resources do you need? I think I'm asking in general to really find out what you want to about Ceres. Now, I'd like to ask a part B too. Could any of this stuff that you're doing inform a rover mission in some significant ways? And if so, could you offer something?
Okay, well that was a simple question. So to answer the first, yeah, we're not handicapped. We are operating incredibly elegantly with 2 reaction wheels and hydrazine jets. So the hydrazine jets, the reaction control system, or RCS. So we can finish our primary mission. If we lost a wheel tomorrow, then we would continue on using our RCS and be able to complete our primary mission without any problem. So we are going to collect all of the data that we planned and that we need to answer these questions. And we are fully funded to analyze those data and put them in the data archive, publish, etc. So there's no problem with resources. Now, if the wheels continue to operate, then it allows us to stay at Ceres, or allows us to have more lifetime. And right now, with fuel on board, we could last without wheels through the beginning of August, and with wheels possibly into about a year from now. So there's quite a bit of uncertainty, but what we are certain about is that we can finish our primary mission. So it's not an issue. And we are working with NASA, and Jim's behind you. He's excited about utilizing these resources to get as much data as we can. Okay, so that said, your last question was about Europa and how can this data inform us about Europa? So I'll say in general, one of the things that we anticipated about Ceres before getting there is that it's a former ocean world. Of course, we're so interested in Europa and Enceladus and these other interesting objects in the outer solar system because we think they harbor subsurface oceans at present and are possible habitable environments and possibly even locations where there's extant life. Ceres appears to have been one of those objects in the past when it was younger and hotter. And what we're looking at now, we believe, is is remnants of a frozen ocean. And so the salt is left over from the brines that were concentrated as the ocean froze out. So it's all a fairly self-consistent story that Ceres is a former ocean world that has where the ocean froze, and now we're interrogating the chemistry essentially of that ocean rock interface through the subsurface layers that we're detecting on Ceres.
I think there's a question in the back.
Yeah, Jacob Aaron, the scientist. Those close-ups of the bright spots in objects created, the red and blues you're seeing, are those the real colours, or are they going to enhance in some way?
I'm going to pass that to Ralf. He wants to know if that's a real color in the on the bright spots. What the colorization of the map.
Well, the color represent first what we see on the surface, but it's not true color. It's also not real color, but it's what the instrument can see. So it's different from what you will see when you are on the surface. But the color differences are weak, but they show up. And as you have seen, it's going in the difference from bright white to blue to brownish colors. And there is obviously something behind this. And the behind this is different of what we know from rocky bodies. It's closer to, coming back to the question before, what we see on icy satellites and even what we see on Europa and also on Enceladus. The big question is what the reason for this color differences is. And for this we probably need to know both informations, and both informations mean the spectral information, both for both of the instruments in order to get what is on the surface, what is a little bit on the subsurface, and we need the imaging and the resolution. And if you remember, when we started approach, then we had Okator as a bright spot. The whole thing was a bright spot. That was amazing, but we had no geologic evidence what it means. And then if we get closer, we see it's not only one spot, it's two spots, and now at the resolution we have now, about 30 meters, we really see it's a geologic feature, it's a dome coming up in the center of this impact crater. So once we have the full information of all of the instruments, I'm pretty sure we will understand what this color differences on the surface are. At this point, it's not clear whether it's compositional, poor compositional, and physical. Physical means some kind of particle size variation or a combination of this. So there's a lot of work to do in order to understand this.
And I'll just point out that the color data is from the framing camera filters, and as Christina pointed out, those are all in the visible spectrum, 7 color filters, and so we really need to interrogate that material with the visible infrared mapping spectrometer to get very detailed information on the composition.
There's a question all the way in the back.
Thank you, David Brown. With respect to sort of working out these myriad mysteries of Akator, what would you say is the biggest missing piece of the puzzle? What data do you desperately wish you had, and can you get that answer from the spacecraft?
Be nice to land there, wouldn't it? Well, I think we need to get. Well, so Christina did touch on this, but the way that the VIR instrument collects its data, it results in many fewer data than we get from the camera. So we've been sort of focusing on the camera data because we have a lot of it. And so VIR is methodically trying to fill in with high resolution all of these targets. And as you can see from the animation at the beginning, we can't always predict ahead while we're sequencing, where the spacecraft's actually going to be over the surface. So it's a little bit of a game of cat and mouse to try to capture some of the high value areas. So we haven't built up the data sets that we would like in Akator. And what is needed is a careful analysis of what you're seeing, right over the dome versus over here, or at the wall or in the surrounding areas, and build up the context. So I think that's one of the key missing pieces right now to putting the story together. And then, as we're seeing even at this meeting, all of the modeling that can try to reproduce what we're seeing in terms of the thermal evolution of the area as a result of the impact process, and what implications there would be for compositional variations in the subsurface to produce mobile materials. So kind of reiterating what I said before, but there's still it's really just still work to be done, because we're not going to get any highly we're not going to get any more data that's extremely different than what we have or plan to get in the near future.
Emily?
There's been, Emily Lockwood from Planetary Society. I've seen a lot of different kinds of flow features being pointed out in talks, and there seem to be a lot of different mechanisms for making these flow features. Can we talk about what kinds of mechanisms seem to be operating in different places? Is there any fluid like people talked about on Vesta, or is it all glacial, or fluidized ejecta, or what?
Okay, in general, we have flow features which are related to mass wasting, flow features which are related to volcanic activity, and flow features which are related to material which is highly volatile. So we see all of them on Ceres, so that makes it in another way unique. Flow features are related to mostly to the impacts we have, but it's not clear what is the material which is flowing. I think we have to really look into the viscosity of these materials. We can distinguish in geology between wet and dry flows. So material which is completely dry but of very small particle size can also flow as very, very, very low particle size sand. So anything can be mobile. The big issue on Ceres is that we see so many flow features on a so low gravity object. So that's a very interesting thing. So that means the material we have is very low viscosity. It has the ability to flow even if there is low gravity. And that is just an issue which had to be investigated in a sense that we need more, not more resolution, but more topographic information in order to understand this, and that's a processing issue. We have the data, but it needs a lot of time in order to really nail down the topographic processing to the order of 35 meters or a fraction of this kind of pixel. And I'm pretty sure we did this for Vesta, and we can do it for Ceres, and we can end up with resolutions, height resolutions in the order of a third of a pixel we have. So, and that's the dimension, that's the scale we really need to understand the flow processes. And once we know the flow processes, we really can say what the material was which has been flown.
Yes.
Eric Berger again. So if I was standing at the base of the Lunar Mons and looking up, it looks, from your images you've shown at 35 meters per pixel, it looks flat, like those surfaces look almost gem-like. If you're standing on the surface looking up at it, I mean, do you have a good guess of what it would look like? And I want someone's wild guess on how this would have been created.
The creation of Lunar Mons is it's a mountain, and the mountain really shows that it has come up from the subsurface. So if you look at it, you really see that the top of the mountains is different from the flanks of the mountain. So that something is coming up from the subsurface and really took the older surface up. So there are two basic theories which can explain this in geology. One is you have some kind of volcanic process. That means some kind of a dike process. Material is really coming up in a very small crack. So we know this from the Earth and from the Moon. That's one solution. We would expect to see much more of cracks there. And the other solution is you bring the material up by diapason. That means if you have a subsurface which has lower density as the surface material, the material will come up. So we know this from salt deposits on Earth. So these two possibilities are, one is density driven, the other one is temperature driven. And okay, we know this processes mainly from rocky material like lava or magma, but we didn't have seen anything so far in, let's say, icy environments. The only thing we know is Enceladus, and Enceladus has a process where it comes out like a geyser. but not as a more viscous material. So we need to look into this more deeply. At the moment, we have evidence for both processes. And so let's say, as nature is, probably it's a combination.
Any further questions? Yes.
May I do a follow-up to that? Is there another scenario where the surrounding area is slumped? Evidence of cracks or...
Yeah, that may be a possible scenario, but there is no real evidence for this. There's an impact crater beside this, but the geologic boundary between the impact crater and the mountain is very clear. So it's really clear that the mountain is younger than this impact crater.
Other questions? Okay, I think this concludes today's briefing. Thank you all for coming. And again, if you would like to download the materials that you saw today, go to nasa.gov/dawn or dawn.jpl.nasa.gov. Thank you.